Hello, DE-FERENCE. My name is Lei Yang. I'm a co-founder and CTO of MegaETH. Today, I'm so excited to be invited by DE-FERENCE and Decipher to talk about how MegaETH solves a fundamental performance problem in EVM blockchain, which is state merklization. We solve the problem with an in-house designed and engineered data structure called Small Authentication Large Trie, or SALT. In this talk, I'm going to show you why existing attempts to fix the state merklization problem have not been so successful, and I'll try to convince you that there's a particular thing that you really need to get right, which is managing sparsity when designing solutions for state merklization. I'll talk about our solution, SALT, and I will try to convince you why it is so optimal in so many ways. But before we dive deeper, a bit of information on MegaETH. MegaETH is a real-time EVM blockchain, and by that I mean the blockchain provides tens of thousands of transactions per second at 10 millisecond block interval. So the benefit is really with these capabilities, application developers can build Web 2 level interactive real-time experiences that you are used to when you just browse the web or use your apps, while retaining the crypto benefits of self-custody, of security, and openness. We just launched our mainnet. Feel free to check out rabbithole.megaeth.com. And on the mainnet, we ran a stress test. Over the period of 7 days, we processed 11.4 billion transactions. At the peak, we processed 55.5 thousand transactions per second, while maintaining the low block interval of 10 milliseconds and the low gas fee of 1/100th of a cent per token transfer. We really think it's the end game of blockchain scaling. And right now on the mainnet, there is a ecosystem of synchronously composable dApps that is forming. So I really encourage you guys to check out rabbithole.megaeth.com for our mainnet. This talk is really about how to speed up state merklization. So let's first take a look at what is merklization. To explain that, I would like to give a quick primer of something called authenticated key value storage. Actually, SALT, the topic of this talk, is itself a form of an authenticated key value storage. So just imagine that you have a database, just a normal database storing data entries. And just for formality, we're going to call each data entry a key value pair. So here, for example, if we say Alice has $10 worth of tokens, and we store this information in the database, then Alice, the name or the wallet address is going to be the key, and $10 is going to be the value. And this combined is a data entry stored in the database. But in addition to just storing the data entries, authenticated key value storage also allows you to compute something called a commitment over the content of the database. You can imagine the commitment to be a hash or a fingerprint or a summary of the content of the database. But in addition, for example, in this case, the commitment can be, say, 0xB for the current content of the database. But in addition, you can also compute something called a proof. And the proof allows you to tell and show anyone and convince anyone that a particular piece of data or a particular key value pair exists in the database corresponding to some particular commitment. For example, this current proof shown on the screen should convince everyone that Alice having $10, this particular data entry exists in the database corresponding to commitment 0x_that. And of course, when you update the content of the database, for example, when you update Alice's account balance, the commitment has to change because the commitment corresponds to a particular snapshot or a particular content of the database. And authenticated key value storage, especially the commitment it produces, are so useful because they can help you prove some state or some particular facts about your blockchain. And this is prominent in use cases like light clients, like cross-chain transfers, like settling states from layer 2 to the layer 1, because it's all about proving that something has happened or some facts are true about your blockchain. For example, the fact that Alice has, say, $20 when she tries to withdraw the money from the layer 2 to the layer 1. And updating, this process of updating the commitment when the content of the database changes is exactly called state merklization. And this verb merklization comes from the authenticated key value store data structure used by Ethereum mainnet, EVM, which is called Merkle-Patricia trie. And here, the verb merklization corresponds to the word Merkle in Merkle-Patricia trie. Okay, now that we saw what state merklization is and how useful it is, let's kind of look at the problem. So what's the problem? The problem here is really state merklization in Merkle-Patricia trie, or the authenticated key value storage data structure used by Ethereum mainnet, is just too slow. So here I'm showing some experimental data. On the x-axis, we're varying the amount of memory made available to our experimental setup. And what we do on this setup, we tell it to process real Ethereum mainnet blocks. And on the y-axis, we measure the amount of time it takes for this block processing pipeline. Especially, we kind of break it down by the different steps. And here, you can see there are 3 steps in general. 1, EVM executes the transactions. Like this is the real useful work, like processing, validating the transactions. The second step, updating the state commitment, or state merklization. And third, writing all this work results back to the disk. So if you compare the purple part and the green part, which is running transactions and the state merklization, you will realize that actually the green part takes the majority of the time, and actually it does. So in the best case, that you have a gigantic amount of memory available to the experimental setup, half a terabyte of memory, merklization is almost 6 times slower than running the transactions. Which means if you spend on average 1 second running the transactions, you will spend almost 6 seconds doing merklization, which is kind of not very useful work compared to actually running the transactions, right? It's more like post-processing, right? And the scenario becomes even worse if you reduce the amount of memory available to the experimental setup to a more practical amount, for example, 8 gigabytes. And in this case, state merklization takes a whopping 10 times longer than actually running the transactions. And this basically means if you don't do anything, if you don't optimize state merklization at all, then you are leaving 90% of your performance on the table. Like there's absolutely no way for you to become faster without actually fixing this problem. Now that we know how severe this problem of slow state merklization is, let's kind of try to dig one layer deep to see why that's actually the case with Merkle-Patricia tries. To understand that, we can quickly take a look at the structure of Merkle-Patricia tries. With Merkle-Patricia tries, you have a bunch of key value pairs, of course, as usual, but you also have a tree structure that is organized in a way that you have a bunch of nodes pointing to each other. Each node has R children, and R is a parameter you can tune, which basically says at most how many children a node can have. And the content of a node is basically the hash of all of its children combined. And the nodes themselves, they organize into paths. So each key corresponds to a path. And you should be able to follow from the root of the tree along the path defined by the key to find out the key value pair corresponding to the path, right? So this is basically the way the tree, especially the internal nodes, are structured. And when you update, for example, here in color red, when you update a particular key value pair, you have to update all the internal nodes traversed on this path from the root to the key value pair. So in other words, all the nodes you kind of hit when you go from the root along the path defined by the key to the key value pair, they have to be updated when you try to do the state merklization after updating or inserting or deleting a particular key value pair. So why is it problematic? It's problematic because you kind of see that to update or just change, delete, modify, add any single key value pair, you are kind of triggering updates to a bunch of internal nodes, and they all have to be written back to the disk when you do the merklization. And disks are really bad at random disk IOs, and this is exactly random disk IOs. It kills throughput because you have to kind of go hopping around the disk to kind of overwrite stuff, it's really slow. So this is kind of the crux of the problem. With Merkle-Patricia tries, each update to the key value pair involves multiple updates to the internal nodes when you do the merklization, and this is the culprit of the slowness. So we now understand kind of the issue of the problem and the root cause of the problem. Let's see if there's any solution. So again, we know the performance issue is really coming from the large number of random disk IOs triggered by merklization. So let's see if we can just minimize the random disk IOs. How do we minimize them? If you want to minimize the amount of data you write to the disk, the best solution is probably just to move the data structure off the disk completely. So in other words, we can try to move the data structure from the disk to the memory of your computer. Because the memory is much, much faster, especially with regards to random writes, we will not hit by the problem anymore. So this sounds very interesting, but we also have to think about the feasibility, right? So what about feasibility? Feasibility is basically you have a very limited amount of memory available to your computer compared to the disk, right? Usually there's no problem for you to get a computer with, say, half a terabyte, 1 terabyte, even 4 terabytes of disk space, but usually with memory size for laptops, usually it's at most 32 gigabytes, and there's a huge difference between the amount of memory available to you versus the amount of disk space, not to mention the price, the cost, right? So it seems that the key goal here is, okay, we want to minimize disk I/O, so we want to fit everything in the memory, but now we are a bit worried if the stuff we have to fit in the memory is too much. So what do we optimize for? The goal here is we should optimize for space. In other words, to store the same number of key value pairs, can we make sure the size of the data structure itself, which stores supposedly non-useful data, is minimized? So the key metric here, as I listed at the bottom of the screen, is the size of the trie, or the size of the blue part, divided by the number of key value pairs, which are actually useful data, right? It's the ratio that matters. So let's first examine if Ethereum's Merkle-Patricia trie is already doing well. Yeah, like spoiler alert, it is not doing very well, and but let's see why. Here, we're looking at a typical Ethereum Merkle-Patricia trie data structure. It uses a parameter of r equal to 16, which means each node can have at most 16 children. And if we do the mathematical analysis, we'll realize that in the ideal case, where each children have exactly the maximum number of children they can have, which is 16, the overall size of the tree should be about 3.2 gigabytes for 1.5 billion key value pairs stored in the system. So 3.2 is pretty fine, and 1.5 billion keys is a lot because it's kind of a decent practical size that we parameterize for, because it's kind of roughly the current recent size of the Ethereum blockchain state. So seems to be fine, right? For the Ethereum blockchain state, you only spend 3.2 gigabytes of extra data stored in the memory. However, this assumption is not realistic. The assumption that each node has exactly the maximum number of children it is allowed to have is not correct. And the reason this assumption is not correct is because of something called sparsity. Sparsity basically says that the deeper you go down the tree, the less utilized the nodes are. For example, at the tip of the tree, at the top, probably you have many nodes having all of their 16 children occupied. But if you go to actually very deep, say close to the actual key value pairs, each node has far fewer of their children slots utilized. The deeper you go, the fewer keys there are per node, and it's harder to fill each node, and the node becomes underutilized. And when the node becomes underutilized, you are kind of wasting space, because previously you are probably handling a lot of children, say 16 children per node, but now some node is only handling, say, 1 or 2 children. It's just much less efficient because you also have to store the nodes themselves. So it's kind of the crux of the problem. We did some mathematical analysis plus experiments. So on this chart, I'm showing you both the theory that we did, which are the curves, the solid curves, and also the experiments, which are the dots. So here what we're comparing is Ethereum's Merkle-Patricia trie data structure, listed as radix trie 16 array, and the optimality, which is the complete tree, which means each node has all of its potential children fulfilled. From the picture, you can see that there's almost a 4 times difference between the number of nodes required divided by the number of useful key-value pairs stored. For radix trie or Merkle-Patricia trie, each key-value pair stored requires almost 0.4 internal nodes being stored as overhead, whereas the optimality is the complete tree, which uses less than 0.5 internal node per key-value pair on average. And let's put some number into perspective. In the previous example where we studied like the case of 1.5 billion key-value pairs, the current size of Ethereum blockchain, now if you consider sparsity, MPT takes 16.8 gigabytes, which is much, much worse than the previous estimation. Now, audience with potential data structure design background might come and say, hey, yes, but usually there's the common wisdom that if your tree is not working well, probably just increase the arity or this parameter R governing the maximum number of children a node can have, right? Because intuitively it kind of makes sense. Because if you have a larger arity, then you can have more children per node, then the tree becomes fatter, but also flatter, and supposedly it should reduce the number of internal nodes needed. So actually, there have been many attempts, for example, vertical tries, pioneered by Ethereum as a potential candidate for replacing Merkle-Patricia trie, although I don't think the plan is panning out, considered an arity of R equal to 256, which is 16 times higher than Merkle-Patricia tries. And also there have been attempts to resize the nodes of Merkle-Patricia tries so that they fit into individual 4 kilobyte blocks for more than SSDs. So for some reason, if you do that, then SSDs becomes slightly faster, right? So the issue with this thought is that when you increase the sparsity, yes, you are kind of trying to make the tree better, but meanwhile, you're also making it even harder for nodes to get filled. Like you're kind of increasing the sparsity, which kind of cancels the benefit. So to justify that argument, we did, yes, some theoretical analysis and experiments, and here we're comparing 3 scenarios. Radix trie 16 array, which is MPT, radix trie 256 array, which is Merkle, and the complete tree 256 array, which is the best that you can hope for. So still, even if increasing the arity from 16 to 256 helped a little bit, they are both still much, much worse than the complete tree, which is the ideal case. And yeah, we saw that increasing from 16 to 256 helped by a little bit, but it actually plateaus in the sense that even if you keep increasing the arity at some point, there is no return, there is no improvement to space efficiency. And this picture shows it. On the x-axis, we are increasing the arity, and on the y-axis, we are recording this overhead metric, right? So realize that this purple curve, which corresponds to radix tries or those MPT/Merkle style tries, if you just keep increasing the arity, the overhead plateaus. The overhead does not keep decreasing. And this is a zoomed out version of the previous chart, so it's easier to see that the benefit actually stops at an early stage as you increase the arity. So in other words, simply increasing the arity does not work. Okay, so at this point, let's try to do a quick review of what we have learned, right? So we started by wanting to minimize the disk I/O doing state merkleization, and our idea is to sidestep this random disk I/O altogether by just storing the entire data structure in the memory. But then we hit a problem, which is to minimize the amount of space taken by the data structure, so that you can fit a lot of key-value pairs into the certain finite amount of memory you have. And we defined that we want to optimize this metric, which is the overhead. In other words, the size of the tree, the internal nodes divided by the amount of useful data or key-value pairs you are storing. And we also made an interesting observation, which is radix tries or vertical tree/Merkle-Patricia tries become sparse and inefficient as the depth increases. So this really hurts the space efficiency for them. Okay, so we kind of saw a bunch of problems, and ultimately it boiled down to sparsity of radix tries. Do we have any solution? So an interesting observation again here is, although yes, radix tries, they are not very good in terms of space overhead because of sparsity, Actually, sparsity are contributed mostly by the lower level nodes. In other words, if you take a look at the higher level, like the level at the root and also a few the immediate levels after the root, they are actually very dense, because that kind of makes sense, right? You only have so few nodes up in the top. It's very easy for a bunch of key value pairs to cover all the potential children they might have. So this picture actually shows the contribution of sparsity from different levels. And the blue color shows the first 4 levels of a radix trie, and the yellow color shows the remaining levels. And after a certain number of keys are inserted, almost all the sparsity comes from the remaining levels. So the way this observation guides us in an optimal data structure design is we realize the top levels are actually fine. They are not problematic. It's actually the lower levels that are horribly inefficient. So our solution, again, and from first principle, is if the top levels are fine and they are not sparse, then you can replace them by just enshrining a complete tree, right? Because they are almost complete anyway, they are not sparse. So we replace the top levels of a Merkle-Patricia trie or any radix tree with a complete tree, which is maximum efficiency in terms of space. And then, because we realized it's the bottom layers that are causing sparsity, we don't use tree-like structure for them. We replace them with compact lists or hash tables that are faster to read, but also does not incur a lot of sparsity, right? It's like really compacted from a tree back into a list. So this is kind of the structure of sort. For the top layers, a static main tree that is complete, and for the bottom layers, a bunch of dynamic buckets storing the actual sparse data. And these 2 pages are basically the textual version of what I described. To insert a new key value pair into a sort data structure, you first go and find the bucket. It's very simple. Basically, you take the hash, you basically randomize your new key value pair into one of the buckets. So once you found your bucket, you just insert your new data into the bucket. And the particular insertion process depends on how you define the buckets. For example, you can tell people that, okay, so my bucket should order the keys from small to large, lexicographical ordering. That's fine. Or maybe you tell people that, okay, so my bucket actually follows some hash table scheme. It's very flexible. Just define some way, some consistent way to maintain the bucket. We don't mandate anything. And finally, once you update the bucket, you need to propagate the hashes back to the root, but fortunately, it's now propagating in the main trie, which is small enough to fit in the main memory. Something very interesting here is that actually the layout of the buckets can be just imaginary. Imaginary in the sense that you can define some canonical or standard version to like order the stuff in a particular bucket, but on the disk you don't have to follow that rule either. You can just put them in some random key value storage, generic key value storage, and this is actually very interesting because now it says you can just use whatever database engine, like whatever the key value storage engine you want to use to implement sort, but not being tied to a particular tailored implementation, which is the case with many other blockchain authenticated key value storage solutions. And actually, finally, the space efficiency is really good because the main tree goes into the memory, it's shallow, it's complete, so it's highly efficient. And then the buckets do not really exist, they just exist in your imagination when you have to like lay out in your mind the keys in the bucket. And then in the key value store, you have the actual data. But it's also compactly managed because you can just have whatever data structure, whatever key value store that you want for the actual pairs of keys. So to quickly recap this, the results, if you use R equal to 256 and D equal to 2, D is the number of top layers you have, the main trie for storing 1.5 billion key value pairs is about 1 gigabyte in memory footprint. And it's really small, and even if you keep expanding the number of key value pairs stored, we will start, of course, expanding the buckets because they cannot no longer hold enough data, but it's also fine. According to the calculation, it does not really incur too much extra overhead. And if we just put sort's space efficiency into the same picture as we showed before, you can see that sort crushed Merkle-Patricia trie as well as Verkle in terms of space efficiency. There's green curve is sort, and it quickly shrinks towards almost zero, almost optimality, once the number of key value pairs surpass about 1 billion to 10 billion key value pairs, which is roughly the order of magnitude currently on those blockchains. And for the main trie, again, there's always zero IO cost to update or to merkleize. And for the buckets, you only need to write whatever key value pair that you are writing, but it's also, you have to do it anyway because you are storing the key value pairs. So this is also optimality. And in terms of computation cost, along the path of updating the nodes and the commitments is also very fast. With 32 CPU cores on a not so fancy server, you can do almost 600,000 key value pairs update per second and keep up with merkleization. So this is some very good results. All right, to quickly recap this talk, we briefly touched on MegaETH mainnet, the real-time EVM blockchain that can process tens of thousands of transactions per second at 10 millisecond block interval. I really encourage you to check out the mainnet at rabbithole.megaeth.com. And then we focused on SALT, Small Authentication Large Trie, which is MegaETH's secret sauce to solve this state merkleization inefficiency. It is the first authenticated key value storage that scales to tens of billions of key value pairs while completely eliminating random disk IOs, which are totally unnecessary during state merkleization. And we talked about our key insight, which is to tame the sparsity when you build your tree. It achieves optimal space efficiency, and it achieves very reasonable computation cost, more than 600,000 KB updates per second with 32 CPU cores. And also the source code of SALT is open source, and it's available at this URL shown on the screen, and I really encourage the people in the audience that are interested to check it out. It's really well organized, it's audited, it's hackable. Just take a look and kind of try SALT for yourself. Thank you very much, and I really appreciate the chance to explain SALT to you and to also introduce MegaETH to you. Yeah, hope you have a good rest of your day.